All right. In this section, we're going to introduce this sort of a really cool and unique way to think about how we represent or how we orient ourselves, um, and and why we don't necessarily always have to orient ourselves in a particular way. Um, in both math and engineering, we sort of stick to our typical or our standard coordinate systems, right? In terms of vectors or in terms of our linear algebra space, we use the I, J, and K vectors to represent our axes, right? So in two dimensions, if I'm on the x-axis, x and y-axis, right? So here's x, here's y in our two dimensions. The I vector is 1 unit along the x direction, and the j vector is 1 unit along the j vector, right? So this would be the vector 1, 0. This is the vector 0, 1. Right, so typical, and you've seen this before, just not in terms of vectors, right? So when we see our typical XY, we think of each one of these tick marks representing one in the X direction, one in the Y direction, and they're sort of scaled in that particular way, right? Um, and then in three dimensions, we add the K direction, which is the Z. So that would be, if we were thinking about this, that would be like up and down. And we do this in order to orient ourselves. So this is how, so using systems like this is how we can end up with things like a negative area, right? If you think to calculus, which you've hopefully taken. In calculus, when we take the area underneath a curve, if I'm anywhere down here, because of our orientation, what we're talking about is because we're below the x-axis or we're down in that negative space, this actually has a negative area. Now, it doesn't actually mean it's negative, it just means that it's oriented below what we call the positive upper space, right? So that's how we can end up with things, with this idea of negative things that don't make sense as being negative, right? Because area represents a physical space. But what we're going to do in this system, or what we're going to do today, is we're going to talk about how to use a basis in order to build a new coordinate system. So we'll get there on that one. But first, we're going to talk just a little bit about bases again. And the first thing we want to talk about is this thing called the unique representation theorem. So I talked about a base or a basis being a set of things, and it's the smallest set of things that would describe that entire vector space if you do the span of it. Okay. Now, and by smallest set, that implies that we're talking about each of those things are linearly independent of each other, or each of the elements. So if I want to talk about some vector in that space, then there's going to only be one set of scalars that's going to give me that exact vector for that basis, right? So each basis gives me a unique set of scalars that would describe the linear combination of our things. So here's what I was going to say. So X is a linear combo of our basis vectors, right? So of our basis vectors. And only one set of scalars is going to get you X. So if you change your basis, so if you change the basis, right? So in the basis videos, we showed that we could have 3 different unique representations for a basis for R3. So changing the basis changes the constants, or changes your changes your scalars, right? So it's not going, so those scalars are not, that represent that vector, are not going to be the same in every basis. So here's an example, and we're gonna look at this sort of visually. We're gonna have some fun here. All right. So all of these are bases for R2. And hopefully you can kind of this makes sense. So right, if we just kind of glance at this, so our standard basis is what happens if you just take the identity matrix, and that kind of makes sense, right? Because I can use the x vector to build anything in the x direction. I can use the y vector to build anything in the y direction, and any combination of those is going to get me any other vector in the plane, right? This other basis, so basis 2 here, I guess basis 1. So standard basis 1, basis 2. Basis 1, you can see, so I have 1, 2, and 5, negative 1. And hopefully you can kind of see that there's nothing I can do to 1, 2 in order to turn it into 5, negative 1. Right? So the only way to get from 1 to 5 by scalar multiplication or addition would be to multiply 1 by 5. But if I multiply 2 by 5, I don't get negative 2. So these two things are linearly independent. Same thing with our basis 2. Negative 1, 1 is linearly independent from 0, 2. Another way that you can kind of think about that is if you graph these, at least in R2, if you graph your vectors and they don't happen to lie on the same line, then they are linearly independent, right? Just sort of by nature. All right, so we're gonna graph these, so we're gonna do our standard basis over here. So standard, we'll do base 1 here, basis 1 here, and basis 2 here. So I'm just gonna graph those vectors, and we're gonna use them to figure out what would I have to do, or how could I get the x vector here based on those vectors. So we'll do, I don't know, we'll do the first ones. Here, we'll highlight. All right, we'll do these ones in red. We'll do these ones in blue, because who doesn't love color coding? So here we have the vector 1, 0. 1, 2 is this guy here. Negative 1, 1 is this guy here, right? And then 0, 1 is this guy here, tiny little thing. 5, negative 1, 1, 2, 3, 4, 5, negative 1, that's this guy here. And 0, 2 is along here. All right. And then I'm gonna graph x in each of these bases. So we'll let x be this lovely little green vector. So that's going to be in the same place for all of these. All right, so here, here, and here. So there's x in all of my bases. So essentially what we want to know is, how can I get x? So what would I need to multiply 3, 2 by? Or in other words, I want to know what are the constants that if I multiply them by my basis, the vectors in my basis, I'm going to get 3, 2 back out. So 3, 2 in this, how do I get 3, 2 out of each of these sets of vectors? All right, so then I have, so here we have the 1, 0 vector, this one's the 1, 2 vector, negative 1, 1, and we got 0, 1, 5, negative 1, 0, 2. So in other words, what is the linear combination of those two vectors that's going to get me the vector 3, 2? And then I guess, well, we'll put some, I don't know, here. Can't really see that, but I need to know what these constants would be in order to get me back to that initial vector. In the standard basis, hopefully it's easy to see that if I scale this first one by 3, if I scale this one by 3, that's going to stretch this guy out over here to 3. If I scale my 0, 1 vector by 2, that's going to stretch this thing out by 2. And if I add them together, my resultant vector is the diagonal of that, in this case, rectangle, right? Can you kind of see that visually? That's what's happening here. Now, B1 and B2 are not as straightforward. In B1 here, I I need to know what is the linear combination that's going to get me 3, 2. So we've already talked about this, right? We've talked about how to get a linear combination, or in other words, we have proved whether or not something is a linear combination of the other things. But here we want to actually like follow through with this and decide what the solution is. So I'm just going to set up an augmented matrix, right? If I set up the augmented matrix 1, 2, 5, -1, and I augment it with what I want to get, the 3, 2, do you see how that's going to get me my solution, right? If you think about this being like an A1 and this being an A2, A1 times that vector plus A2 times that vector needs to equal 3, 2. So we want to solve for the A1, A2 vector. So it's the same thing as solving the AX equals B. It's all the same thing. Same thing, different day. All right, so if I augment this, and again, I'm going to let you do those row operations on your own and come out to it, but we end up with the reduced row echelon form, where the RREF comes out to be this lovely little vector here. So what that says is that A1 is going to equal 11/9, and A2 is going to equal 4/9. So here we'll get rid of those guys. And we'll replace, so if I take 11/9 times my 1, 2 vector and 4/9 times my 5, -1 vector, and I add them together, I'm going to get my resultant 3, 2 vector. So hopefully you can kind of see that. So the 11/9, which that's just a smidge over 1 of those things. And the 4/9, oh, I also totally graphed that wrong. Didn't I? Oh, I just made a hot mess of things. That wasn't supposed to be 5, -1. That was supposed to be 1, 2, 4, -1. Also, I can't graph. Oh, that's why. That makes no sense. The 5. Oh goodness, guys. I should edit more often. This should be a 4. Make that a 4. It really, honestly, it doesn't matter if it's a 5. It just changes my math down here. Actually, let's make it a 5. We're going to come back. I'm going to fix that. Okay. And hopefully you're at home screaming, no, no, no. If that's a 5, those are not the numbers. And we'll just go back there. Also, hopefully you're also screaming, that's not how you graph 1, 2. It's been a day, guys. Long day. All right, so this is correct. That's correct. But 1, 2 goes like that instead. Phew, that makes more sense. All right, and then 5, -1. So here I'll RREF that and come back in a second. It was close. All right. With the 5, not the 4 that I had in my notes that I apparently did not copy down into my vectors properly. We get 13/11. Oh, that's the wrong color, isn't it? We get 13/11. Ay, 13/11 and 4/11. Right, so still saying that our first vector, so this one's 13/11, this one's 4/11. So that's saying that this red vector, we're going to take just a smidge more, right? So we need just a smidge more. And if you think about this, it needs to be the resultant of a parallelogram, right? When we add two vectors together, the resulting vector is the diagonal of the parallelogram. So this looks like it's roughly 4/11 of the vector to get me that. This, I need to go just a little bit extra, so I have to scale it by 13/11 to get just that smidge further. And hopefully that makes more sense. Okay. You try B2 on your own. You tell me, what do I need to multiply the first vector and the second vector by in order to represent my vector 3, 2. So try this on your own. Come back. That one was much better. That one was actually correct in my notes. Correct basis. Cool. All right. So this one says that I would need, in order to, I actually need to, notice I need to reverse the direction of my first vector in order to have my resultant be, and then here's my lovely, lovely parallelogram. So I need to scale this guy by 1.5 or by 2.5, right? So I need 2.5 of them. So there's one of them, there's another half of them to get me where I need to be. And then I need to scale this guy back by 3. So 1, 2, 3, and that'll get me my resultant vector. So those are all different representations of the same vector for a different basis for R2. So we're going to come back to this idea in the next video.